previous modules, we have encountered different examples of curves. Now, with the mathematical techniques that we have studied, we are going to explore with more detail one of them, the helix. A circular helix is a space curve that can be thought as a trajectory of a particle that follows a helicoidal movement. That is, the particle rotates around an axis, and at the same time, it moves along that axis. On the screen, we have the case in which the axis of rotation is the z-axis. Therefore, the x and y components of the parametrization represents a circle, the rotation movement, and the z components give us a translation, the translation along that axis. If the helicoidal movement follows the right-hand side rule, we obtain a destrogyrous helix, and we have a levogyrous helix in the other case. You can see the parametrization of both cases on the screen. There are several examples of helices in nature. A famous one is the double helix structure of the DNA strand. Notice that the two helices that form the DNA strand are destrogyrous. In architecture, we can highlight the DNA tower in Perth, Australia, inspired by the DNA strand. Or the Pozzo di San Patrizio, St. Patrick's Well, a historic well in Orvieto, Italy. The central well shaft is surrounded by two spiral ramps in a double helix, which allowed mules carry the water downward and upward directions without obstruction. Or finally, the staircase of double helix of the Vatican Museum in Rome, designed by the architect Giuseppe Momo. The circular helix has an interesting geometric property. We first find the tangents of the helix by computing the derivative of the parametrization alpha. Then, the angle between the tangents and the z-axis is constant, as the dot product or inner product of alpha prime and the vector 0, 0, 1 is always 1. This means that all the tangents have a constant inclination with respect to the axis of the helix. We consider this geometric property of the circular helix to define a more general space curve, the generalized helix. A space curve is called a generalized helix if its tangent vectors form a constant angle with respect to a fixed unit vector u. If the curve is parametrized by the arc length, but that's equivalent to saying that the inner product of alpha prime and u equals a constant, that constant is the cosinus of the angle between the tangents and that unit vector u. In the case of regular curves, we have a result obtained by Lancret in 1802. This result says that the curve is a generalized helix if and only if the torsion function and the curvature function are proportional, being the cotangent of the angle the constant of the proportion. We can check the Lancret theorem in the case of circular helix with parametrization the one you have on the screen. We compute the derivative, that is the tangent vector. And we can check immediately that the tangent vector satisfies the helix condition, that is, the inner product with respect to the vector 0, 0, 1 is constant. And also, the Lancret theorem condition is satisfied, that is, the curvature and the torsion are proportional. We can obtain a generalized helix starting from a plane curve by considering the following construction. We begin with an arc length plane curve alpha, and we define a space curve beta where the z component is proportional to the arc length parameter s. Then, it is easy to check that the tangent vectors satisfy the helix condition. We can also study generalized helices lying on a sphere. In this case, these curves must satisfy the helix condition given by the Lancret theorem and the spherical condition over the curvature and the torsion given by the equation you have in the center of the screen. By considering both conditions, we obtain that the curvature function must satisfy the ordinary differential equation you have at the bottom of the screen. This differential equation might be complicated, but we provide now the solution of it. The curvature function and the torsion are the ones you have in the blue boxes on the screen. We now develop an example of this situation. we consider the cardioid with parametrization x, y, and 0, where x and y have the expression you have now on the screen. Then we consider a space curve beta with parametrization x, y, the components of the cardioid, and the z component proportional to cosinus of t over 2. We now check that this curve is a spherical curve and a generalized helix at the same time. From the expressions of x and y, after some computations, considering the trigonometric relations of the double angle, we get the relation you have at the end of the screen. And considering also the expression of the z component, we get that x, y, and z satisfy the equation of a sphere with center the origin, that is the point 0, 0, 0, and radius 3. Therefore, the curve lies on that sphere. We now compute the tangent vector of that curve. For that, we calculate the derivative of the parametrization and the modulus of that derivative. The tangent vector is the quotient of the derivative by its modulus, and this tangent vector turns out to have a constant z component. Hence, the inner product of the tangent vector and the vector 0, 0, 1 is constant. Therefore, we have a generalized helix on a sphere constructed from a cardioid. We finish this video with two curiosities. The first one comes from nature. The narwhal is a type of whale with a long tooth shaped like a levogirus helix. Some rare specimen has two teeth of this type, both levogirus. That fact breaks the principle of symmetry in nature. The other curiosity comes from the ancient Greece. The Archimedes screw is a machine historically used to transfer water from a long line body into an irrigation ditch. It consists of a cylinder with a helix inside. Turning the screw in the downward direction, the helix drags water from the low to the high deposits.